Hello and welcome to our 19th session. In today's session we're going to continue our discussion of the p-n junction diode in equilibrium. There are no applied biases. There's nothing moving. It's just sort of sitting there. But there is an internal electric field and there is a depletion region and there is a potential, all centered around the metallurgical junction, the point where the P and the N come together. And we're going to be looking at those quantitatively in this session, and there'll be a little bit of mathematics, but I'll try to explain it in a way which is not too painful. So first we're going to listen to a wonderful performance of Rodgers and Hammerstein's Oklahoma. Okay, and we'll see you in about 3 minutes.
It ain't too early and it ain't too late.
Starting as a farmer with a brand new eye.
Soon be living in a brand new state.
Brand new state.
Gonna treat you great. Gonna give you barley, carrots and potatoes.
Pasture for the cattle.
Spinach and tomatoes.
Flowers on the prairie where the June buds soon. Plenty of air and plenty of room.
Plenty of room to swing a rope.
Plenty of heart and plenty of hope.
Oklahoma, when the wind comes sweeping down the plain, and the waving wheat can sure smell sweet when the wind comes right behind the rain. My honey lamb and I sit alone and talk, watch a hawk making lazy circles in the sky. We know we belong to the land, and the land we belong to is grand. And when we say, I am my own, yeah, we're only saying you're doing fine, Oklahoma, Oklahoma.
Okay, so this is a broad outline of some of the topics we'll be covering today. I'd like to start off with a review of the electric fields in a qualitative sense in both the Schottky and the p-n junctions. We'll specifically be highlighting the differences between these two structures. And then we'll go on to look at things that we've already seen qualitatively, specifically the depletion region in p-n junctions, the electric field in p-n junctions, and the built-in potential VBI in p-n junctions but instead of qualitatively, we'll actually be looking at them quantitatively, deriving some of the expressions, and there'll be a little bit of mathematics involved in this. And as you can imagine, the basic tool in our toolbox will be what will it be? It will be Poisson's equation. Poisson's equation is what is going to allow us to develop these relationships. And then we'll be looking at an example of graded doping. Till this point, all the doping has been such that the charge density has been constant. And if the charge density is constant, the electric field is linear and the energy is quadratic. If the charge density itself is linear, the electric field is quadratic and the energy is cubic. So we'll be doing one example where we show that. Okay, so we'll start off with the electric fields in the Schottky and in the p-n junction. First, in the Schottky, this is an n-type Schottky rectifying junction. I know it's rectifying because the bands bend up. The electric field is negative because in the depletion region we have positive donor ions. So the electric field goes from plus to minus in the negative direction. The electric field in the metal, which is this region here, is precisely zero. The electric field jumps rather dramatically at the interface, jumps down, and then decreases in magnitude as we move into and through the n-type depletion region. There is a characterization here of a sharp corner right at this point. In the p-n junction, there is no sharp corner. The electric field is zero in the bulk, which is over here, and then when it gets to the edge of the depletion region, it slowly drops down, reaching a maximum at the metallurgical junction right here, and then decreases in magnitude until it again becomes zero at the bulk n-type. No sharp corner. And, well, is that a big deal? Yes. Sharp, not good. Smoother is better. Okay, so now let's look at the depletion region in a quantitative sense. This will be the depletion region dimension, the total depletion region from this point to this point. This is the total depletion region dimension. And that will be W. VBI is the total band bending from this point to this point, and it's a function of the dopings both in the acceptor side, the P side, and in the N side. This is the formula that we'd like to derive, and we're going to do it. In this case, we're going to start with the form. We're actually going to derive this when we talk about the built-in potential. But the form we had for the Schottky barrier is this equation here. And if we look at the N side, it is exactly the same. So I'm not going to derive this right now. I'm going to just write it down. And this will be the depletion region only, and I didn't change the notation here, but we're going to logically dope this stuff out. W here in this case is the depletion region width only in the N-type. VBI is the band bending only in the N-type silicon. There's another part of this for P-type. This actually, I probably should have put WN here because WP would be the depletion width in the P-type silicon, and instead of ND, I would have N sub A. Now this equation right here says that the depletion region on the P side is equal to the depletion region on the N side scaled by the doping. if, for example, the doping on the N side is large compared to the doping on the P side, then WP will be much larger than WN. The larger depletion width always goes with the lighter doping. And we see that from this figure right here, which shows the charge density. This would be heavily doping on the P side, lightly doping on the N side. The areas under these two curves, however, are exactly the same. For every positive ion on the N side, we have a line of force which ends on a negative ion on the P side. So every line here, which starts from N, ends on P, the total number of charges, which is to say the total areas, are equal, and this equation is basically just a representation of that fact. Okay, so we're going to start with example 1, which will allow us to develop the equation that we seek, which is here, 10.3. Actually, this should be 11.3. I'm sorry about that. It's chapter 11, not chapter 12. Okay, so the total, we start with the total band bending is equal to the band bending on the N side, added to the band bending on the P side, and this very important equation which scales the depletion region widths as functions of band bending. So we can substitute for WP, and we get an equation which only involves Wn. So wherever we see WP, we substitute Nd divided by Na multiplied by Wn, and we solve now for Wn in terms of BBI and the dopings. And that is this equation, P1.4. Okay, so now what we do... Okay, so actually, before we continue on here, we could also solve for, let's see, we could solve for Wn, and we could also eliminate Wn and solve for WP. These equations are not particularly useful. I'm not even quite sure how I included them here, but it's okay. Anyway, I'm not sure we're going to use these. Anyway, what we do is we start with a rather trivial equation here, which is just a restatement of Wn plus WP is equal to the square root of the squares. That's why I have a 3 lines here. This is an identity. But this allows us to expand the Wn and the WP in somewhat more detail. So we just use simple algebra here. And, oh, actually, we do use these. Sorry about that. So we do use P14 and P15. I actually substitute those in for Wn and WP in terms of the dopings. So, no, okay, I wasn't that silly after all. So substituting Wn squared for here, we just square this part, and that's this. And then WP squared is this, and then 2 times WA multiplied by WP. So now this, this square root sign is this square root sign here. So now we have the total depletion width as a function of a constant term. This would be the total band bending at the 2 dopings Na and Np, and our job is to take this guy under the square root sign and use some algebra to massage that. Well, the way to do that, as you can imagine, is to get a common denominator, and the common denominator is all of this stuff in the bottom. It's right here, and then we get 3 separate terms, 1, 2, 3, just by using basically combining fractions. We're just combining 3 fractions to get 1 fraction here. And now we're going to massage this a little bit further. And notice that this is just Na plus Nd squared on the numerator. Cancel out one of the Na plus Nd on the denominator. So I get square root of Na plus Nd divided by the product of Na and D, and that is equal to 1 over Na plus 1 over Nd, and that is the equation that we see. That is this equation right back here. So we've been able to derive equation 11.3 by using some relatively straightforward algebra arithmetic combining fractions. Okay, so now we're going to go on to the electric field, and we're going to actually develop the equations for electric field using our most important tool in the toolbox, Poisson's equation. And we're going to apply Poisson's equation on both the P side and on the N side. On the P side, we know that the charge density is negative. Where is that? Someplace up here. Charge density on the P side is negative. The charge density on the N side is positive. And that's why we have minus Q on the N side, Na, and on the right side we have Q and D. So we can integrate Poisson's equation simply substituting for rho, taking the dx, integrating. We of course have an epsilon on the bottom. Since the charge density is constant, we just get a linear equation, which we suspected, and here it sits. This is a definite integral, but we're going to basically make it a little bit more general by writing it as an indefinite integral and then applying the boundary conditions. So at 0, at the metallurgical junction, this is a mistake. This should not be 0. This should be x equals minus WP. And of course the electric field is 0 at x equals minus WP, and that allows us, we just basically put in 0 here, allows us to calculate C1, and we get the final expression for the electric field in the P side, and it is linear, and at x equals minus WP, it is 0 as it should be. Okay. It is negative, and its slope is negative. And that is exactly as it should be. On the N side, we have the same procedure. We have another constant of integration, and this is the electric field in the N side. It's also negative, and at x equals Wn, it is 0. At x equals 0, it is the maximum value. And here we see the figure for the electric field in the P side and in the N side. 11.11, the field at 0, we can equate these two at 0. Both the electric field in the N side and the electric field in the P side become equal at the metallurgical junction, and the electric field is maximum at that point. Okay. So our next topic is the built-in potential, VBI or PBI, if we're talking about the energy band diagram. Just 2 corrections before we trudge on to that and attack that. There should be a minus sign here because at x equals 0, the field is maximum, but it's maximum in a negative sense. And there's another little problem over here. It's maximum negative, and in equation 11.3 0.9, that was a minus sign. It should be a plus sign. So I've corrected both of those. And the reason, of course, is that the slope is positive. Okay, so now let's talk about the built-in potential. So we start again with Poisson's equation, but instead of saying d E dx is equal to rho, we say E is equal to the derivative of the voltage or the potential or the energy. And if we wanted to relate this to charge density, this would be the second derivative. Okay, so we're going to take the electric field, which you've already found, and on the P side, we're going to go from the depletion region edge minus WP to anywhere in X. We're going to keep it as a indefinite integral. And we're going to say that is the potential or the voltage as a function of X. So then the question comes up, where do we choose the zero value? Now, we don't have a choice. If it's the electric field, the zero is determined for us. But in voltage or energy, it's all relative. So we can choose it wherever we want. And we're going to choose it at the depletion region edge minus WP. That'll be our zero. And that kind of makes sense. We're going to choose it way out here and there. So, oh, that certainly doesn't look zero. It seems like it's going down. Well, that's one of those little pesky things that we know that on the energy band diagram, as you go down in energy, the voltage goes up. The voltage becomes more positive. And again, as we've mentioned a number of times, the reason is because the energy band diagram is reference to the electron energy, not the whole energy. So we're going to choose the energy of zero here, and then all the energies are going to go up in the positive y direction. Okay, so we put the electric field into this integral. What's the electric field? It is someplace. There it is. Oh no, that's for the inside. This is for the p side. So we put this in and we integrate. We get an x squared, and here that is. Simply x squared for the first term and x for the constant term, and then of course we have a constant of integration, and the constant of integration is determined by saying that x equals minus WP, the energy will be zero. That's right here. And then doing that, we determine C1 very easily. So we get finally that the voltage in volts, not in electron volts, not in joules, not an energy band diagram, it's the mirror image of the energy band diagram, is equal to this expression 11.15, and it goes up. It starts at 0 when x is equal to minus WP, and it goes up, and it goes up in a parabolic way, and that's important. And that is, of course, exactly what happens here, except it goes down in a parabolic way. Okay. Now, on the N side, we have the same thing. We put in the electric field that exists on the N side, which is right here. We integrate that bad boy, and we get a quadratic term and a linear term and another constant of integration, C2. And how do we determine C2? Well, we determine C2 by matching the voltage at x equals 0 on the N side to the voltage at x equals 0 on the P side. So we put in here x equals 0. That must be equal to Vn of x equals 0, and that allows us to determine C2 relatively straightforward. We put in C2, And this is the voltage on the inside here, and it has a constant term which we obtain by matching the voltages at the P side and on the N side at X equals 0. So the total voltage, we just add these two bad boys up. This is the P side. Where's the P side? This is still the N side. This is still the N side. It's got three terms. There they are, 1, 2, 3. And no, I'm sorry. I apologize. This is not the entire voltage. This is the voltage at X equals Wn. So at X equals Wn, we put in Wn here, we put in Wn here, and this is a constant term. And what do we find? Voila! We find it is the total band bending, exactly what we had previously, which we derived. Well, we didn't really derive it. We derived it using thought processes, and here it exists as a complete derivation using Poisson's equation. Now this suggests an alternative way of doing the same thing without doing nearly as much mathematics. We can start with the potential on the N side, and we know if we start with the potential, or the voltage I should say, voltage and potential are generally synonymous one with another, but not energy. Energy measured in electron volts, again, is the mirror image. So if we start with the voltage on the N side, we know that as X increases, the voltage will decrease. And that's what we're saying here. It decreases with a square law dependence, and on the N side, of course, it only depends on Wn. We don't have any P doping or Wp. So the dependence is only on the N side doping. The only way to satisfy these conditions is if we let V sub n be equal to the total band bending minus how much we lose on the N side as X increases. So if X increases, the minus sign here says that the voltage will decrease the maximum minus the stuff that decreases on the N side, and of course the decrease is parabolic, and we satisfy the boundary conditions at X equals Wn. We have V sub n equals VBI, because all this term goes away, and at X equals 0, we have, put in X equals 0 here, we have equation 1123, and then we have the expression that we derived using a fair amount more of mathematics. So this is kind of an alternative derivation which uses combination of mathematics and logic. Okay. And here we see the voltage, again, not the energy. The voltage on the P side goes up, so that at the metallurgical junction, we have this value right here. And on the N side, it goes down. Notice that it does not start at 0. Where does it start? It starts from here. That's where it starts. So this point right here is this point, as explicitly shown in the diagram. And the total voltage is equal to VBI, which in volts is equal to the band bending if we use electron volts or joules. Now if you look at the Schottky, this is an N-type Schottky, again, voltage, not electron volts, not energy, but voltage. So the N side bends down. It pains me to say that, but that's true if we're talking about volts and not energy. So on the Schottky, it's a single-sided barrier, but on the Schottky, instead of ending up here someplace, it ends at x equals 0. It ends at or begins, if you will, at voltage equal to 0. Okay, so if you've been listening to the sessions, you know that I am a units fanatic. So this is a little bit of a note on units. And if we go back to the energy band diagram, we've seen this expression quite a bit, going back to previous sessions, that the energy bending is equal to KT over Q multiplied by the log of the doping divided by N sub I. This particular one is for an acceptor. That's why it's NA, and that's why this is VP and not VBI. So let's just look at the units. So the units here are NA over NI. That is unitless. They are both in numbers per cubic centimeter. The units of KT are joules, KT over Q electron volts. Same thing as joules. So that's basically what we show here. That does not look like, and this I'm just using the P side here because it's just, I want to compare the acceptor to acceptor. Does this look like anything that looks like this? Well, we know this is electron volts, and we have a feeling that this is going to be volts. Well, let's take a look at some of these units here. QNAWP squared. Q is just electronic charge. This is charge per cubic centimeter. So this is charge per cubic centimeter times square centimeters, which would be coulombs, charge per centimeter. The units of permittivity are coulombs per volt centimeter. So we find that we just divide this by this, and indeed we find that V and P is equal to the same units as V and, in this case, of 0. It doesn't matter. It could be any X. That's irrelevant. But the units are volts, because we have coulombs per centimeter divided by coulombs per centimeter divided by volts, and the volts goes upstairs. So all of this thing works out to volts. Is it the same as this? It's pretty darn close, but it's not exactly the same. Volts are, as we know, joules per coulomb. Okay, so now let's do one more example. This is going to be a blast from the past, so to speak. We're going to go back to a Schottky. We could do it for PN, but it would be a little bit more complicated, a little bit more involved. So let's go back to the Schottky, an N-type rectifying metal semiconductor structure with two profiles. This is the standard profile that we've been using until now. ND is constant. It's an N-type semiconductor. So we have doping in the donors and D, and that's a constant. But then we're going to introduce something new. Instead of being just a constant A, it's going to be a constant A multiplied by X, which means that if X equals 0, there is no doping. But as we go deeper and deeper into the semiconductor, the doping gets greater and greater and greater. This is called a linear doping profile. Okay, so we're not told the metal work function. We don't need it. All we're told is the doping profile, and this one will be straightforward, just to review, and this one will be a little bit newer. Just to kind of think about this thing, we know that if the doping profile is constant, the electric field is linear and the energy is quadratic. We're going to then kind of suppose or conjecture that here the electric field is going to be quadratic and the energy is going to be cubic. So let's see if that indeed is the case. So again, we use our standard toolbox kit here, the Poisson's equation, and in the first case, rho will be just a constant A. Relatively straightforward. We take it out of the integrate, we take A out of the integral, we get a linear function, and we notice that the function is, electric field is negative, which we've seen many times, and it has a positive slope because as x increases, the electric field increases. Okay, for a linear grading now, instead of A, we have AX. We integrate this guy, and we get indeed a quadratic. And going now to the energy, we integrate the electric field, and the electric field for the constant doping is just W minus X, and indeed we get a quadratic. Substituting the boundary conditions, I won't do that. I won't go into all the details here, but hopefully you can follow. This is not all that difficult. And of course, we get the standard relationship of the depletion region dependence on the band bending that we've seen quite a number of times. For the linear grading, we put in the quadratic electric field, and indeed we get a cubic, and now the depletion region width, it's one-sided, so I don't have to say WP or WN, it's just W because it's only one band bending side, and that's in the N silicon, only one depletion region. But notice the dependence here, it is cubic. So if you compare 215 to 212, instead of having a 2, we have a 3. Everything else is the same, and we have a 1/3. So that's pretty neat. And we do find that linear gratings are quite common in modern day devices. Okay, so finally, let's compare the Schottky and PN rectifying junction. I should say comparing the Schottky rectifying and the PN junction, because PN junction are always rectifying. So you'll excuse my stupidity there. This rectifying should go over here. So flip that. Schottky rectifying and PN junctions. Okay. So for the Schottky, this is the schematic. This is the picture of it, and we have that sharp discontinuity. It doesn't jump, but there's a sharp corner at the metallurgical junction. In the PN junction, there is a smooth transition. So these are the energy band diagrams for the Schottky barrier and for the PN junction. And if you look at the comparison here, the Schottky junction, this is Schottky junction with N silicon. PN junction, we have P. Let me correct that right here. That should be P silicon on the left, P silicon on the left, and N silicon on the right. So that's a little bit more clear. We could have it the other way around, but generally we put the P on the left and the N on the right. The metal work function in the Schottky is greater than it is for silicon, so the Fermi level in the metal goes up as we go to equilibrium. The P side, you see, I don't have to worry about it, because the P side always has a work function greater than the N side, because P Fermi level is closer to the balance band. So that's why this is always rectifying, and this, depending on the metal, can be rectifying or not rectifying, depending on the metal work function. Big metal work functions, bigger than silicon, rectifying. Small metal work functions, probably not rectifying. Okay. Equilibrium achieved by bringing up the metal Fermi level. In the case of the PN junction, the bands bend up on the N side and down on the P silicon side. And the Schottky electrons transfer from the N metal, from the N silicon to the metal. In the p-n junction, electrons transfer from N to P, and holes transfer from P to N. And as we mentioned, the electric field has the sharp corner at the junction because the metal is a field-free region. Here the electric field is nice and smooth, and that's good. But the slope of the electric field is always positive in an N-type Schottky. The slope of the electric field is positive on the N side, as we've seen many times before, and is negative on the P side. Okay, so that's pretty much what we wanted to accomplish. And we can give ourselves a pat on the back, and that was pretty good. And now let's enjoy a marvelous clip this is from the BBC Proms from Rodgers and Hammerstein, South Pacific, one of the most beautiful love songs ever written. Some enchanted evening, and we'll see you next time.
One waits so long for what is good, and when at last it comes, one cannot risk to lose, so one must speak and act quickly, even if it seems almost foolish to be so quick. And that is the way things happen sometimes, isn't it, Nellie?
Yes, it is, Emil.
Some enchanted evening, you may see a stranger. You may see a stranger across a crowded room, and somehow you know even then that somewhere you see her again and again. Some enchanted evening, someone may be laughing. You may hear her laughing across the crowded room, and night after night, as strange as it seems, the sound of her laughter will sing in your dreams. Who can explain it? Who can tell you why? Fools give you reasons, wise men never try. Some enchanted evening, when you find your true love, when you feel her call you across a crowded room, then fly to her side and make her your own. Oh, for your life you may dream all alone. Once you have found her, never let her go.